All right. Thank you so much for inviting me. I'm very happy to be here. And today I'll be talking about Sailfish, a latency efficient DAG-based protocol. So this is joint work with Nibesh and Aniket. So we've been talking about multiple proposers, and DAG-based protocols are, a natural way to have multiple proposers. So the talk will be split into two parts. The first part of the talk, I'll try to compare and contrast, DAG-based protocols with leader-based protocols and try to see, what the differences between the two are. And this will be the smaller portion of my talk. And in the second part of my talk, I will talk about, this protocol itself and an analysis on this protocol. So the problem we're talking about is state machine replication, where there are a group of parties who agree on a sequence of transactions submitted by external clients. And they do this even if some of these parties are faulty. Okay, so you have transactions coming in one at a time, they agree, and they output these blocks. There are two key properties that we are looking for, safety and liveness. Safety says that two non-faulty parties do not disagree. And liveness says that a transaction proposed will be eventually executed. So we want to achieve both of these properties, safety and liveness, even when some of these parties may be Byzantine. So let's say some T out of n, up to T out of n parties are Byzantine. And you want this to hold under different network conditions. So the network condition of interest over here for us is going to be partial synchrony, where the network can be asynchronous for a while, but eventually it is synchronous. And it is customary to solve this problem for T less than n over 3 under partial synchrony. And if you look at this historically, there are two key metrics that people have tried to optimize. One is latency and one is communication complexity. So latency says that the time to commit a latency is the time to commit a client transaction, and communication complexity is the amount of communication and bits that happens in between parties. And if you go back to the literature and look at all of the protocols, you would find that most, at least many of these protocols, they have an approach which follows, roughly speaking, the phase king paradigm, where there is a designated party called as the leader, and the leader is responsible for proposing blocks of transactions and getting all parties to agree on them. Okay? If the leader is malicious, of course, you cannot expect progress. But if the leader is honest and if the network is good, then you expect progress as well as safety. So many protocols such as PBFT, Tendermint, Hot Stuff, Pala, and so on, follow this structure. And in fact, if you look at the latency and communication complexity metrics, PBFT already gives you from 2000 gives you ideal latency. Hot Stuff 2 give you ideal communication complexity. So then a natural question is, aren't we done? Do we need anything more? Well, what about throughput? So intuitively or theoretically, we always we relate communication complexity and throughput, right? So if you have low communication complexity, it implies, you can get a high throughput. But in leader-based protocols, it turns out that your leader can be a bottleneck, okay? And this can happen in two different ways. So first concern over here is unequal scheduling of work, where you can have a leader, let's say, you have a 1,000-party system, and let's say in a vanilla leader-based protocol, it is sending a 1 megabyte block. So if it is sending to 1,000 different parties, then it is sending effectively 1 gigabyte worth of information. But if you look at this from the perspective of individual parties, they're only accepting 1 megabyte worth of information. So there is unequal resource usage in that sense. And second, if the leader fails, of course, we'll change the leader and eventually the protocol will progress. But for that time being, there is no progress that happens. So because of these reasons, despite having good communication complexity, we may not have good throughput. And these are known problems with leader-based protocols, and there have been approaches to improving throughput. So there are notions called as extension protocols, where you extend 1-bit consensus to L-bit consensus. And the key idea over here relies on erasure coding techniques to improve throughput. So there is this other line of work called data availability oracles. Dank sharding, tiramisu are examples over here. Even over there, they rely on erasure coding techniques. In fact, the first two lines of work, they are similar. It's just different names by different groups of people. There is a different technique called narwhal, which is a systems level optimization that separates transaction dissemination from consensus. So you rely on different worker nodes to actually transmit data. So all of these approaches really do help in improving throughput. So this new line of work on DAG-based protocols actually, address both of these concerns in a more natural manner. And they do this by ensuring that every party performs a similar amount of work at all points of time. So because they're doing similar work at all points of time, it fundamentally solves this unequal scheduling problem that we were discussing earlier. And second, because your DAG construction itself does not rely on the leader, so you have a situation where even if a leader fails, the construction proceeds, and eventually you will see progress. So the disadvantage, though, is since everyone is working at all points of time, you do have high communication complexity. So before we move on to talking about our protocol itself, I want to make one comment on the terminology itself. So both of these terms, leader-based or DAG-based, they're actually misleading terms. If you think about it, many leader-based protocols construct chains, which are DAGs, and DAG-based protocols typically rely on leaders to achieve consensus. So in my view, the key properties that are achieved by DAG-based protocols are the two properties that I described earlier. And while leader-based protocols can give you these properties in some ways or some subset of these properties, DAG-based protocols give them to you in a very natural manner. With that, if you look at existing DAG-based protocols, they give you improved throughput at the expense of communication complexity for small to moderate-sized settings. But they do not achieve ideal latency. And that was the focus of our work on Sailfish. So we asked, can we obtain DAG-based protocols with ideal latency? So in the following, I'm going to describe the core structure of a protocol. And I'll tell you at a high level what the core safety argument is, and I'll show you a couple of graphs on performance. Okay, so it's a DAG-based protocol, so everyone is maintaining a DAG. So what you see to the left over here is the frontier of the DAG for a given party at the end of round R-1. Okay, so you move from round R-1 to round R. So party, let's say the first party over here, proposes a block. It points to 2t plus 1 vertices from the previous layer. And similarly, other parties will propose similar blocks. Okay, so over here, when I say you're pointing to 2t plus 1 vertices delivered from the previous round, I mean it in a very specific sense, where this delivery happens by a reliable broadcast protocol. So you propose it, you pass it through a reliable broadcast, and once the reliable broadcast protocol ends, it delivers. That is when we call it as delivered. And this, it turns out, it gives you two nice properties. One is non-equivocation, and one is totality. So non-equivocation says that if I have delivered a block from a given party in a given round, no other party will deliver a different block by the same party in the same round. And totality says that if once I have delivered a block, everyone will deliver this block eventually. So together, what this ensures, if you apply this for every vertex, what this ensures is that eventually every party is going to build the same DAG. Okay, so if everyone is going to build the same DAG, aren't we done? Don't we have agreement? Why do we need any consensus? Well, if you look at the view of any party at any point in time, that may be different. Eventually they're going to be the same for a given round, but for now they may be different. So as an example, the view of party Pi over here at round R may be that it has received the first 3 vertices, but not the last one. And for Pk, it may be the case that it has received 1, 2, 4 and not vertex 3. Eventually they'll receive it, but if I have to order right now, that may not be the case. And this is why we need agreement on whether a vertex is delivered. So how do we obtain consensus and order these vertices? In our protocol, we have these designated parties called leaders. So the vertex that has a symbol, the leader symbol on it, is the leader for that vertex. And let's assume that everyone knows who the leaders are for each of these rounds. So our goal is to commit a leader vertex in any round. So if I'm committing a leader vertex in round R, what we do is all of the parties in round R+1, they prioritize pointing to the leader vertex in round R. So they will wait for the leader vertex until some timeout and make sure that they point to it. If it doesn't arrive by then, maybe they won't, but until then, they will try to prioritize pointing to the leader vertex. Okay, and if it so happens that this leader vertex in round R, let's call it vertex V, if it receives more than 2t plus 1 votes, or there are more than 2t plus 1 vertices from round R plus 1 pointing to it, then we can commit this leader vertex. And this is when I'm going to order some vertices in the past. Okay, so you do this in 2 steps. The first step is you try to find path to a leader vertex in previous rounds, so the largest previous round, and you try to recursively commit vertices in that round. So as an example over here, this round R leader vertex is pointing to this round R minus 1 leader vertex. So you try to recursively commit this round R minus 1 leader vertex if you haven't done so. And then you order all of the vertices that remain that are still pointed to by this round R leader vertex. So you can apply any deterministic ordering that you prefer. So that's the protocol over here. There's just one step that I haven't mentioned. So you prioritize pointing to the leader vertex. What if the round R leader is Byzantine? We know that because we are using reliable broadcast, it cannot equivocate. But what it can do is, it can feign a crash. It can ensure that you do not receive this delivered block at all. No, perhaps no one receives it. So if a round R leader vertex is not delivered in a given amount of time, let's say until some timeout, all of these parties send a no vote message to the next leader. And this next round leader, round R plus 1 leader, would use a certificate of 2t plus 1 parties stating that we haven't voted or we haven't delivered this round R leader. So it uses this to justify the fact that this round R leader does not exist. So if from round R plus 1 leader's perspective, either I point to the previous leader or I show this certificate saying that this leader does not exist. Yeah, so that's the protocol. And the safety argument over here is actually quite neat. So let's look at, if we want to ensure everyone has the same ordering, what do we actually need? So the core guarantee we want is the following. Let's say there is some vertex, some party that has committed a round R leader. Okay, and let's say there is some other party who has not committed this round R leader by satisfying the rule that we described earlier, because maybe some vertex was not received in time and it could not see the 2t plus 1 votes. But it commits some other vertex in a higher round R prime. Okay, what we want to ensure is that both of these parties order all of the transactions that they have received in the same order. Okay, and because when we are committing this higher round leader vertex, we are trying to find a path to a previous leader. What we want is to ensure is that this path really exists. Okay, so if some party commits a round R leader vertex, then there is a path from round R prime leader vertex to this vertex, and this should hold for any higher R prime. Let us see how we can satisfy this claim, and we'll do this in 2 parts. We'll first talk about when R prime is the immediate next round, and then we'll talk about any higher R prime. Okay, so when R prime is the immediate next round, observe that there are 2t plus 1 votes from around R plus 1 on around R leader vertex. And out of these 2t plus 1 votes, t plus 1 of them are coming from honest parties. And since if they vote, they will not send a no vote message to the next leader, a no vote certificate cannot exist that is sent to the next leader. And if the next leader has to exist, it has to point to this round R leader vertex, because it only has 2 options, either show a no vote certificate or point to the previous leader vertex. So for this reason, it has to point to the previous leader vertex. So this is part 1. For an argument for higher rounds is simple, and I'll show you an argument for R plus 2, and for R plus 3 and so on, the same or a similar argument actually holds. Over here, we are interested in 2 different quorums. The first quorum over here is Q1. So in round R, So in round R plus 1, observe that 2t plus 1 parties are pointing to this round R leader vertex. And let's say this quorum is quorum Q1. It is denoted in orange color, right? If I look at the leader vertex in round R plus 2 now, it also has to point to 2t plus 1 vertices in round R plus 1. Right? So this is denoted using the green arrows, and let's call this quorum Q2. Okay? So the two quorums Q1 and Q2 has to intersect in t plus 1 vertices. And out of these t plus 1 vertices, up to t may be Byzantine, and there has to be at least one honest vertex, because of which there will exist a path from the leader vertex in round R plus 2 to the leader vertex in round R. So that's the core safety argument for the protocol. In terms of latency, what a leader vertex of round R gets committed in round R plus 1. So essentially it's two RBCs, but it turns out that you don't need to wait until two RBCs are done to actually commit this leader vertex. In fact, because of the way our quorums are aligned, for the second in round R plus 1, you can actually commit as soon as the first message in the RBC is received, because of which the latency to commit is 1 RBC plus 1 delta. Okay, and for non-leader vertices, when you commit round R leader vertex, you commit non-leader vertices from round R minus 1 as well, and they were proposed one round earlier, so that's why it requires one additional RBC to commit them. So the key advantages of Sailfish are, it's the latency. You achieve 1 RBC plus 1 delta and 2 RBC plus 1 delta respectively. And this is better compared to all prior work. Second, the protocol has a leader in every RBC round. So this is compared to state-of-the-art protocols like Shoal. This improves on the latency of non-leader vertices. And finally, the architecture over here, by relying on RBCs, it simplifies things quite a bit compared to works like Cordial Minus and Mysticity, which open all of these black boxes. So the final thing that I want to mention is the performance results. We spoke about things happening in theory. Can we observe these latency advantages that we see in theory in practice? Okay, so we compared our results with Bullshark and Shoal, and we set up, we actually modified Bullshark's code to accommodate Sailfish. And we set up our experiments in such a way that all of them were geo-distributed in 5 GCP regions. And here's a quick graph that we have. On the x-axis, you have throughput, and on the y-axis, you see latency. There are 3 different curves over here, one for Bullshark, one for Shoal, and one for Sailfish. So the way these experiments are performed is, you keep adding more and more transactions to the system until the system, so initially the system can handle it, and that's why your latency stays flat, even when your throughput is increasing. And at some point, the system cannot handle it, and at that point, all of the transactions are buffering, and eventually the latency shoots up. So you always see these hockey stick curves, and what we're interested in is the inflection point. Okay, so because this is a throughput versus latency curve, higher throughput and low latency is good. So to the right and lower is good. And as you can see with Sailfish, with the blue curve, you see it is to the right and lower than the other two. And in terms of how does it scale with respect to the number of parties? Over here, we conducted these experiments for different network sizes, 10, 20, and 50. And as you can see, everything that we said in terms of latency holds true as we scale n as well. So on the y-axis, you have latency, and the blue line is always lower than the orange and the red line. Okay, so with that, let me conclude my talk. So we first spoke about DAG-based protocols. We observed that the key things that they give you are equal scheduling of work and progress at all times. Then we spoke about Sailfish, which runs in RBC-based rounds, and we saw that it achieves a latency of 1 RBC plus 1 delta and 2 RBC plus 1 delta for leader and non-leader vertices respectively. And there's a third part which we actually did not discuss in the talk, that is supporting multiple leaders in a given round. Thank you, and I'd be happy to take questions.
Hi. So there is a theoretical minimum latency in which consensus can be run, at least with this failure tolerance. And if I recall, it's about the same as the theoretical minimum latency for RBC. So is there any hope for getting the latency for something like a DAG-based protocol like Sailfish down to the theoretical minimum for consensus, or is there a fundamental difference between the latency these kinds of things take?
So the theorem minimum latency for consensus or Byzantine broadcast in partial synchrony is 3 delta. And over here, 1 RBC, if you assume a latency efficient RBC, it's 2 delta time. So 2 delta plus 1 delta is 3 delta. So over here for leader vertex, we already achieved theoretical minimum latency.